A-level physics lesson 51, Momentum and Impulse. At GCSE level, you learnt that momentum, given the letter P, I'll write this down, in fact I'll write this at the top, momentum P is equal to mass multiplied by velocity for a body. And that is still the case, that is still true. That is how we define momentum. In classical physics, it is the mass of a body multiplied by its velocity. And that's it, we've done. No, not quite, there's more. We need to move on to A level. So Newton's three laws can be written in terms of momentum. Newton's first and second law we're going to be looking at in this lesson, and Newton's third law will come up. I don't even think it's next lesson. I think it's the lesson after that. We really do save the best for last. So Newton's first law, expressed in terms of momentum, is that if the resultant force is equal to 0, then the rate of change of momentum is equal to 0. And so I've written that as d by dt p. So I could write that in a slightly different way so that rate of change is all kept together. D by dt of p is equal to 0. But remember that d by dt was the rate of change. So d by dt equals the rate of change. It's divided by time, which is what makes it a rate. And for discrete changes, we can instead write delta by t. So for discrete changes, we can say that resultant force the resultant force is 0. Let's just get rid of that. Then we could say delta p divided by t equals 0. Change of momentum divided by the time it takes to change that momentum is equal to 0. That's what we mean by discrete. Discrete is some measurable chunk, some measurable change, rather than a continuous change, which is what the d by dt is all about, a continuous change. So that's Newton's first law. So let me write that as a number 1, rather than just a bullet point. Number 1, Newton's first law is if the resultant force is 0, then the rate of change of momentum is 0. So Newton's second law is, for all other situations, is that the resultant force is proportional to the rate of change of momentum, d by dt of p. And that's why you can see that when the resultant force is 0, then obviously the rate of change of momentum has to be 0, because the two are directly proportional. We do actually take a step further, and we say the constant proportionality is 1, defining the unit of the Newton. So you can take any proportionality, we can take any proportionality and we can make it an equation by using a constant of proportionality. Proportionality just means if you plotted a graph of the rate of change of momentum versus the resultant force, you'd get a straight line passing through the origin. That's what we mean by that proportionality symbol, that thing that looks like a left-facing fish. So the constant of proportionality is 1, defining our resultant force, or stating that it equals the rate of change of momentum, d by dt of p. And again, sometimes this is written as dp by dt. I prefer to write it slightly separate, mainly because the mathematicians or should I say the students of mathematics who learn calculus first from mathematics don't realize that these two are actually completely equivalent. And whilst it's true that d by dt is some sort of function or gets treated as a function, we can manipulate it in certain ways in physics and in mathematics. It's just they don't. Anyway, there we go. That is for continuous changes. Well, remember that P equals mv, so we can actually take this a step further. We can say, what if the rate of change of mass of a body does not equal, let's actually start with what if that equals 0? What if the mass stays constant? That's what we're saying, i.e. constant mass. Well, in that case, we can expand our proportionality. Now, this goes a little bit further than A-level, not a lot further, and it is stuff that you do in A-level mathematics, but it goes a little bit further than A-level physics. I'm not going to use the delta anymore. I'm going to say F is the result of delta, I mean sigma. I'm not going to use the sigma anymore. I'm going to say F is the resultant force. And if we say this is equal to d mv by dt, that's equal to m dv by dt plus v dm by dt. I think it's called the product rule or something like that. I'm no mathematician, so if I've got that wrong, get in the comments and let me know. Helps my engagement. Right, so if dm by dt is equal to 0, then all of this term becomes 0. So that then turns into just m dv by dt, and dv by dt is by definition acceleration. So we end up with F equals ma for constant mass. And that's where it comes from, using this product rule. I think it's called the product rule. On our calculus, on our dp by dt. If you're just using discrete changes, you kind of lose this, this effect. You don't realize that this is what's actually happening. But a little bit of calculus, not very much, just a little bit of calculus reveals all this. Now what that means is that when we don't have constant mass, so what if dm by dt does not equal 0? In other words, there is a changing mass, i.e. changing mass. Well, what do we do then? Well, then we just use that full equation. And it's not easy. I'm not going to pretend it's easy using m dv by dt plus v dm by dt. I'm not going to pretend it's easy to use ma plus this other term, because v is a function of t. It's changing because we're accelerating, dm by dt. So when we integrate, we're going to have to deal with the fact that we've got this changing velocity over time and a changing mass over time. So it can get a little bit more complicated, and we have to jump into some calculus that's beyond A-level to be able to solve problems analytically where there's a changing mass. But even if we don't do that, even if we just look and see that we've got this term and this term, we can see that if the mass is reducing, like this, if we have a reducing mass, that's going to have this term decreasing. But if we've got constant force, that means this term must increase. And if that term's increased, that means the acceleration will increase as the mass decreases for a constant force. It does all kind of fall out of that equation, and we can see what happens as the mass decreases to the rate of change of that increase in acceleration. But I have got somewhat ahead of myself, so let's bring it back to momentum and impulse. Momentum is mass times velocity in classical physics. Yes, I know that we've already looked at momentum in quantum physics and in relativity, where it is not mass times velocity. In fact, we could write there our momentum is equal to our Planck's constant divided by the de Broglie wavelength. But that is a link to, that's non-classical. That's a link to non-classical physics. So we're not going to be looking at that in this topic. We're going to be doing classical physics. Okay. Well, that's momentum covered. What about impulse? That's in the title as well. Well, impulse is just a fancy name for the change in momentum. Hence why I sometimes call Newton's second law impulse rate, because the rate of change of momentum, and change of momentum is impulse. So impulse is change in momentum by definition. Easy as that. Let's put a box around that. Let's put a nice big red box around that. That's quite important. It's a new key word. That is what impulse is. And we go back to black. Good. Well, so what? Well, so let's imagine a reimagining, if you like, our equation. Rather than writing F is equal to dP by dt, let's change that, let's transform that into F dt is equal to dP. Now, there are only certain circumstances where you're allowed to do that. This is one of them. Don't let the mathematicians tell you can't split it because dt isn't a variable, it's part of the differential function. I mean, they're right, but in this circumstance, you absolutely can do that. And we can then do something like this. So adding up all the small changes in momentum, adding up the small changes in time multiplied by the force, which is possibly constant, but not necessarily. Force might be a function of time. Now, if the force is constant, in other words, if, let's change color pen, let's say if d resultant force by dt is equal to 0, in other words, the force is a constant, then we can take that outside the integral and get f, and then we have integral dt is equal to integral dp, which that just is the force multiplied by the time it takes is equal to the change in momentum. And I am going to put this as a delta p. It is a change in momentum. Now, why is it a change in momentum? Because there is another term which I haven't included, the plus c term, the constant of integration. And so that should be included in there as well. But I'm not going to go into that, so I don't need to. I can just present it like this. And then you can fight it out with your maths teachers later on. Where's that constant of integration? It is right there in that delta. So this, you can see, is the same as we had. Ft equals delta p is no different to what we had for the discrete version of Newton's second law. The discrete version of Newton's second law up here, no, where was that? That was when the resultant force was 0, wasn't it? So the discrete version was just going to be delta p divided by t equals f. Delta p divided by t equals f. And what we got here, delta p divided by t is equal to f. So this only works for constant force. So let's draw a graph of constant force. A situation with constant force. So we've got our y-axis and our x-axis. And our y-axis is going to be labelled with force, and our x-axis can be labelled with time. And we have a constant force, so that is going to be a line with 0 gradient, just like that. And the value that this force is, let's call it F, the resultant force. And let's say that we have that force applied for an amount of time equal to t. Just like that. Well, in that case, because F times by t is equal to delta P, it is just that F here multiplied by this T here, which is the area of this shape. Now, I know this is because it is a constant force, so the shape is a simple rectangle, but area of graph between line and x-axis. I'll write the word and. Now, this is no different to other situations where we've had to calculate areas. If you remember the displacement from a velocity time graph, we calculated the area. And if the area was above the x-axis, then it was positive. If it was below the x-axis, it's negative. And that area represents the amount of momentum that has been transferred. Now, that's for nice regular shapes. And next lesson, we'll look at situations where we do not have a constant force. We have impact forces that change over time. But for this simple illustration to start us off with, I think this is okay. We can say that the area of a force time graph is equal to the impulse. So if we have a force applied, but for a very small amount of time, we don't actually have that much change of momentum. If we have a very small force applied for some amount of time, then we get a small change of momentum. A small force applied for a long amount of time, that's a bigger change of momentum. And this is how things like solar sails work, or are proposed to work. They, depending on when you watch this video, we might be using that technology. There's a very small force due to the momentum that light carries and the light being incident on the solar sails. And I'm talking about spacecraft. And if we want to change the momentum of the spacecraft, change the direction they're moving in order to avoid meteors, or would there be meteors if they're up in space? No, there'd be asteroids. To avoid asteroids, or if we need to make a course adjustment to do a slingshot maneuver, so we need to change the momentum somehow. Remember, momentum is a vector. It has a direction as well as a magnitude. So let's say we want to change the momentum, either the magnitude or the direction of that momentum of a spacecraft, but we've got all the time in the world to do it. We could use a solar sail, and over a long enough amount of time, even though it's only a small amount of force that is going to be exerted, it can cause considerable changes of momentum. Up in space, of course, we don't have air resistance to contend with, and we have that luxury of time. So that is what impulse is, just the change of momentum. We could write it if we wanted to, and I'm just going to throw some maths up here. We could write that the resultant force, which was the change in momentum divided by time, and this is for a constant force. Remember, if this only applies, if we've got deltas, it's a constant force. So we could write that as the final momentum that the body has, subtract the initial momentum. U is initial velocity, remember, divided by time. Or we could factor out the m if we wanted to and say mv minus u, and use that to calculate the change in velocity of a body. And so we could take this a step further. If we want to know what the change of velocity of the body is, we could say that v minus u is going to be equal to ft divided by m. And I'm not going to be able to write every possible way we can rearrange these equations. There's lots of terms. We can rearrange them a lot of ways. But you can see that if we have the force acting for a long enough time, we have a big enough change of velocity. We want a smaller mass, bigger change of velocity, and bigger force, bigger change of velocity. Okay, we've looked at what happens if mass is constant. What if the mass changes at a constant rate, but we keep the velocity the same? So a constant velocity. It's a bit of an artificial situation having a constant velocity, but if we've got a constant velocity despite a force acting, then there must be some other force acting to make the resultant force zero. So here we'd be using this equation and looking at, I'm talking about this equation, I'm drawing a circle around here, and we'd be looking at one particular force, but not the resultant force, and the effect that has. If dv by dt is equal to 0, then this whole term is equal to 0, and then we've got a constant velocity multiplied by a rate of change of mass. Now, you can get that with rockets taking off, for example. So if I take the example of a rocket launch. Let's suppose we have a rocket which is launching at a constant velocity. It's ascending at a constant velocity. So assume, let's get the pen, assume constant velocity rocket launch. Just like that. If it's a constant velocity and it's not, if it's constant velocity, then the resultant force will be 0. But we can look at what force must be acting if we're losing mass of the rocket, which is what we're doing. So we could say fuel, mass of rocket reducing because of using fuel or using the propellant, using fuel propellant or propellant fuel propellant. So in that situation, we've got our equation. Resultant force is equal to v dm by dt plus m dv by dt, but that term is equal to 0 because we said we've got no acceleration. Because the acceleration is equal to 0, then this term is equal to 0. So the equation simplifies to F equals v, which is a constant v now, dm by dt. So this is the force that is produced by that rate of change of mass, or should I say that rate of change of momentum, due to the fuel being ejected out the back rather than making the fuel go any faster. How on earth am I going to word that? So this is the force due to expulsion of mass at particular velocity. So the mass is being expelled, particular velocity, and the rate of change of that mass is what's going to cause the propellant force. If that's equal to the air resistance plus the gravitational force, both of which would be acting in the opposite direction to the rocket launch, then the resultant force of the rocket is 0. But that doesn't mean the velocity is 0. And in order to keep that velocity, we have to keep on chucking mass out the back. So that's kind of how a rocket launch works. And hopefully that's enough detail about that, because I really don't want to go into any more detail. Rocket launches don't happen at a constant velocity, so it's a bit of a fudge, isn't it? Let's just draw a quick rocket. Ooh, lovely. And we've got this coming out the back. And what we've got coming out the back is, of course, there's an amount of mass that's coming out per second, which is that. And then we might have a constant velocity of the rocket relative to the air, and well, we're actually interested in the velocity of the fuel that's coming out, the exhaust. It's that v in that equation, and we really do need to start looking at Newton's third law now, because that means that this exhaust experiences a force equal to F. But what about the force on the rocket? And that's where we need to talk about Newton's third, spell third right, third law. So I really hope we'd look at Newton's third law next lesson. No, we don't. We'll talk about impulse more next lesson. Okay, 2 more lessons. Anyway, that's the end of this lesson. Hope you found that helpful.